Welcome to a peaceful journey through our home galaxy, the Milky Way. Get comfortable, let your body relax, and allow your mind to drift as we explore the gentle wonders of the galaxy we call home. Close your eyes if you'd like, and simply listen as we travel together through the stars that surround us. Our galaxy is called the Milky Way because of how it appears in the night sky. On a dark, clear night, far from city lights, you can see a pale band of light stretching across the sky like spilled milk. Ancient civilizations saw this glowing river and told stories about it. The Greeks thought it was milk from the goddess Hera. Other cultures saw a path for spirits or a bridge between worlds. But what you're really seeing is the combined light of billions of stars, so many that they blur together into a soft glow. You're looking at our galaxy from the inside, seeing the disk edge on. And it's one of the most beautiful sights nature offers. The Milky Way is home to somewhere between 100 billion and 400 billion stars. The exact number is hard to pin down because many stars are hidden behind dust clouds and others are simply too faint to count. But imagine that number for a moment. Hundreds of billions of stars, each one a sun, many of them with planets orbiting around them. Our sun is just one star among this vast multitude, and Earth is just one small planet circling that one star. We're part of an enormous cosmic family, billions of stellar siblings sharing the same galactic home. Our galaxy is shaped like a flat disk with a bulge in the middle, and it's absolutely massive. If you could travel at the speed of light, it would take you about 100,000 years to cross from one side of the Milky Way to the other. The disk itself is relatively thin compared to its width, only about 1,000 light-years thick in most places, though the central bulge is thicker. Imagine a dinner plate with a fried egg in the middle, and you have a pretty good idea of our galaxy's shape. We live out in the disk, about halfway between the center and the edge, in what astronomers call a comfortable, quiet neighborhood. The Milky Way is not alone in space. It has companion galaxies, smaller galaxies that orbit around it like moons orbit a planet. The two largest are the Large Magellanic Cloud and the Small Magellanic Cloud, visible from the southern hemisphere as fuzzy patches of light. These dwarf galaxies are slowly being pulled apart by the Milky Way's gravity. Streams of stars being stripped away and absorbed into our larger galaxy. It's a gentle process happening over hundreds of millions of years, galaxies merging in slow motion, a cosmic dance that will eventually make our galaxy slightly larger. At the very heart of our galaxy sits a supermassive black hole called Sagittarius, a star. It has a mass of about 4 million times that of our sun. compressed into a region smaller than our solar system. This might sound frightening, but it's actually quite peaceful. The black hole sits quietly at the galactic center, and its gravity is what holds our entire galaxy together. All the stars in the Milky Way, including our Sun, orbit around this central point. It takes our Sun about 230 million years to complete one orbit around the galaxy. Since the Sun formed about 4.5 billion years ago, it has made roughly 20 trips around the galactic center. And Earth has been along for the ride every single time. The space between stars in our galaxy is not completely empty. There are vast clouds of gas and dust drifting through the Milky Way, and these clouds are where new stars are born. One of the most famous is the Orion Nebula, a stellar nursery about 1,300 light-years away, where dozens of new stars are forming right now. You can see the Orion Nebula with your naked eyes as a fuzzy patch in Orion's sword, hanging below his belt. Inside this glowing cloud, gravity is slowly pulling gas together, compressing it until it becomes hot and dense enough to ignite nuclear fusion. Stars are being born as you listen to these words. A process that's been happening throughout the galaxy for billions of years. Our Sun is not where it was when it formed. Stars don't stay in one place, but drift slowly through the galaxy. Their orbits influenced by the gravity of other stars and the overall mass of the galaxy. Over the billions of years since the Sun was born, it has traveled thousands of light years from its birthplace, and all of its original stellar siblings have drifted away in different directions. We don't know which stars formed from the same gas cloud as our Sun. They're scattered throughout the galaxy now, strangers who were once family, each following their own path through space. The Milky Way has spiral arms, curved structures that wind outward from the central bulge like water spiraling down a drain. Except these spirals are frozen in space, moving so slowly that their shape remains constant for millions of years. Our solar system is located in a minor spiral arm called the Orion Spur, situated between two major arms named Perseus and Sagittarius. These spiral arms are not solid structures, but regions where stars and gas are more densely concentrated than average. As the galaxy rotates, matter moves through these arms like cars moving through a traffic jam. The arms themselves don't rotate as rigid structures, but persist as density waves, regions where material temporarily bunches up before moving on. There are globular clusters orbiting our galaxy, spherical collections of hundreds of thousands of stars bound tightly together by gravity. These clusters are ancient, some of the oldest objects in the Milky Way, containing stars that formed when the universe was young. The stars in globular clusters are packed much more closely together than stars in the galactic disk. If Earth were located in a globular cluster, our night sky would be filled with thousands of bright stars, and there would be no such thing as true darkness at night. The sky would glow constantly with starlight. These clusters orbit in a halo around the Milky Way, some coming close to the galactic center, others swinging out to enormous distances before returning. The oldest stars in our galaxy are about 13 billion years old, almost as old as the universe itself. These ancient stars formed from the material created in the Big Bang, mostly hydrogen and helium, with almost no heavier elements. They're called population 3 stars, though we've never actually found one. The stars we can see from Earth are younger, made from material that's been enriched with heavier elements from previous generations of stars. Our Sun is a relatively young star at only 4.5 billion years old, made from recycled stellar material that contains carbon, oxygen, iron, and all the other elements necessary for planets and life. The Milky Way is moving through space at about 1.3 million miles per hour relative to the cosmic microwave background. That's the speed at which our entire galaxy is traveling through the universe, carried along by the expansion of space and the gravitational pull of other massive structures. We're not just orbiting within the galaxy, we're being carried through the universe by the galaxy itself. Every star in the Milky Way shares this motion. All of us traveling together through the cosmos like passengers on an enormous ship sailing through an ocean of space. Asterisk. There are stellar streams in the Milky Way, long ribbons of stars that mark the paths of smaller galaxies and star clusters that have been torn apart by our galaxy's gravity. These streams wrap around the Milky Way like threads, the remains of smaller galaxies that ventured too close and were pulled apart by tidal forces. The stars from these disrupted galaxies continue to orbit the Milky Way, but they're now spread out in long, thin lines that trace their original orbit. Our galaxy grows by consuming smaller galaxies, a process that's been happening for billions of years and will continue far into the future. The central bulge of our galaxy is crowded with stars. Near the galactic center, stars are packed much more densely than in our neighborhood. If we lived near the galactic core, the nearest star to our sun might be only a light year or less away, instead of the 4 light years to Alpha Centauri that we have now. The night sky would be spectacular, filled with bright stars. But there would also be more danger from nearby supernovas and other violent events. We're fortunate to live in a quieter region where such dangers are rare. The Milky Way has a warped disk. If you could look at our galaxy edge on from a great distance, you'd see that the disk doesn't lie in a perfectly flat plane, but has a gentle S-curve to it. This warping is probably caused by gravitational interactions with our satellite galaxies. The large and small Magellanic Clouds. These smaller galaxies pull on the outer parts of the Milky Way's disk, distorting its shape over time. The universe is not made of perfect geometric forms, but of shapes that bend and flex under the influence of gravity. Our galaxy is full of planets. Since astronomers began discovering planets around other stars in the 1990s, we've found thousands of them, and it's now clear that most stars have planets. Current estimates suggest there might be more planets than stars in the Milky Way. That means hundreds of billions of worlds circling other suns, each one unique, each with its own characteristics. Some are gas giants, larger than Jupiter. Some are rocky worlds like Earth. Some orbit close to their stars where temperatures are scorching. Others orbit far out where it's frozen and dark. The variety is endless, and we've only begun to explore this planetary abundance. There are stars in the Milky Way, moving at incredible speeds, racing through the galaxy at hundreds of miles per second. These are called hypervelocity stars, and they were likely flung out of the galactic center by gravitational interactions with the supermassive black hole. They're moving so fast that they'll eventually escape the galaxy entirely, becoming lonely wanderers in the space between galaxies. Right now, these stars are still part of the Milky Way, but they're on their way out, destined to become intergalactic travelers in the distant future. The disk of the Milky Way is where most of the star formation happens. New stars are being born constantly in the spiral arms where gas and dust are compressed by density waves. Our sun formed this way about 4.5 billion years ago, condensing out of a cloud of gas and dust that had been enriched with heavy elements from previous generations of stars. The planets formed from the leftover material, small worlds built from the debris of stellar birth. This process is happening right now in stellar nurseries throughout the galaxy. New solar systems forming, new worlds being born. There's a phenomenon called galactic habitable zone, a region of the galaxy where conditions are most favorable for life. Too close to the galactic center, and there are too many dangers like supernovas and intense radiation. Too far out toward the edge, and there aren't enough heavy elements to form rocky planets. The ideal zone is roughly where we are, in the middle regions of the disk. Far enough from the center to be safe, but close enough that there are plenty of heavier elements available for planet formation. Of course, this is based on life as we know it. The universe might be more creative than we imagine. The Milky Way contains neutron stars, the collapsed cores of massive stars that exploded as supernovas. These objects are incredibly dense, packing more mass than the sun into a sphere only about 12 miles across. A teaspoon of neutron star material would weigh billions of tons on Earth. Some neutron stars are pulsars, spinning rapidly and sending out beams of radiation that sweep across space like lighthouse beams. When these beams point toward Earth, we detect regular pulses of radio waves, some pulsing hundreds of times per second with incredible precision. These cosmic lighthouses mark time with their steady rhythms. Natural clocks scattered throughout the galaxy. There are binary star systems in the Milky Way, where two stars orbit each other, bound together by gravity. About half of all stars in our galaxy are part of binary or multiple star systems. These paired stars can have fascinating relationships. Sometimes they orbit close together, whipping around each other in hours or days. Sometimes they're far apart, taking centuries to complete one orbit. If one star is much more massive than the other, it will evolve faster and might transfer material to its companion or even engulf it. Binary stars lead complicated lives, their fates intertwined by gravity and proximity. The Milky Way has suffered collisions in the past. About 10 billion years ago, a smaller galaxy called Gaia Enceladus merged with the Milky Way, and stars from that ancient collision are still part of our galaxy today, though they've long since mixed with the rest of the stellar population. These collision events are violent in the sense that they involve entire galaxies merging. But remember that galaxies are mostly empty space. The stars themselves rarely collide. They just get mixed together, forming a new combined galaxy with stars from both original galaxies, blended into one population. There are brown dwarfs in the Milky Way, objects that are too small to be stars, but too large to be planets. Brown dwarfs form like stars collapsing from clouds of gas. But they don't have enough mass to sustain hydrogen fusion in their cores. They glow faintly from their leftover heat of formation, slowly cooling over billions of years. Brown dwarfs blur the line between planets and stars, reminding us that nature doesn't always fit into neat categories. The universe creates objects of every possible mass, filling in all the gaps between tiny planets and massive stars. The Fermi bubbles are enormous structures extending above and below the center of our galaxy. Lobes of high-energy gamma rays that stretch for about 25,000 light-years in each direction. Scientists think these bubbles were created by a period of intense activity from the supermassive black hole at the galactic center millions of years ago. Perhaps when it consumed a large amount of matter and belched out jets of material. These bubbles are invisible to our eyes, but glow brightly in gamma rays, marking a time when the heart of our galaxy was far more active than it is today. The Milky Way is part of a larger structure called the local group, a collection of about 54 galaxies bound together by gravity. The three largest members are the Milky Way, Andromeda, and Triangulum, with the rest being smaller dwarf galaxies. These galaxies orbit each other in a complex dance, their mutual gravity binding them together into a cosmic neighborhood. The local group is itself part of an even larger structure called the Virgo supercluster, and that's part of the Laniakea supercluster. We're nested inside structures within structures, each level adding more context to our place in the universe. There are stellar nurseries throughout our galaxy where new stars are being born at this very moment. The Eagle Nebula, about 7,000 light-years away, contains the famous pillars of creation, towering columns of gas and dust where stars are forming. These pillars are several light-years tall, enormous structures where gravity is slowly compressing gas into new suns. Baby stars are hidden inside these clouds, still gathering mass, not yet hot enough to ignite fusion. They're stars in waiting, preparing for the moment when they'll begin to shine. The Milky Way is constantly renewing itself, creating new stars to replace the old ones that die. The disk of our galaxy rotates, but not like a solid object. Different parts rotate at different speeds, with the inner regions completing their orbits faster than the outer regions. This is called differential rotation, and it's why the spiral arms exist. If the galaxy rotated as a solid disk, the arms would wind up tighter and tighter over time until they disappeared. Instead, the spiral pattern persists because it's a density wave, not a physical structure. Matter flows through the arms, bunching up and then spreading out again, maintaining the spiral pattern even as individual stars and clouds move through it. There are magnetar stars in the Milky Way, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. These are the strongest magnetic fields known anywhere in the universe. The magnetic field of a magnetar is so intense that it warps the atoms around it, and if you got within a few hundred miles of one, the magnetic field would disrupt the molecular bonds in your body. Fortunately, magnetars are rare and far away, exotic objects that remind us how extreme conditions can become in the universe. Even something as invisible as magnetism can reach incredible intensities under the right circumstances. The halo of our galaxy contains dark matter, an invisible substance that doesn't emit light or interact with normal matter except through gravity. We know dark matter exists because of its gravitational effects on stars and gas in the galaxy. The visible matter in the Milky Way isn't enough to hold the galaxy together, given how fast it's rotating. There must be additional mass providing extra gravity, and that mass is dark matter. It forms a spherical halo around the galaxy, extending far beyond the visible disk. We can't see it directly, but we can measure its influence. this invisible glue holding galaxies together. Asterisk. There are planetary nebulae in the Milky Way, beautiful shells of glowing gas expelled by dying stars. When a star like our Sun reaches the end of its life, it swells into a red giant and then gently puffs off its outer layers, creating an expanding bubble of gas that glows as it's energized by ultraviolet light from the hot core of the dying star. These nebulae come in many shapes, some spherical, some hourglass-shaped, some with intricate patterns and structures. They're some of the most beautiful objects in the galaxy, and they represent a peaceful ending for stars like our Sun. A gentle dispersal of material back into space where it can eventually be recycled into new stars and planets. The youngest stars in our galaxy are hot and blue, burning their fuel at a furious rate. These massive stars shine brilliantly but live fast and die young, exhausting their nuclear fuel in only a few million years. When they die, they explode as supernovas, spectacular events that briefly outshine entire galaxies. These explosions are violent, but they're also creative, forging heavy elements in the intense heat and pressure and scattering them into space where they can be incorporated into new stars, new planets, and eventually new life. Every atom of carbon in your body, every atom of oxygen you breathe, was created in a star and scattered by a supernova. You are made from the ashes of stellar explosions. There are circumstellar disks around young stars throughout the galaxy, flat pancakes of gas and dust orbiting newly formed suns. These disks are where planets form, material gradually clumping together into larger and larger objects until planets are born. Our solar system formed from such a disk about 4.5 billion years ago, and we can now see similar disks around other young stars. Watching planet formation happen in real time. The Milky Way is full of planetary systems at all stages of development, from disks just beginning, to form planets, to mature systems like our own, to ancient systems where the star has already died and only the planets remain. The Milky Way will eventually collide with the Andromeda Galaxy. Andromeda is currently about 2.5 million light-years away and moving toward us at about 70 miles per second. In about 4 billion years, the two galaxies will begin to merge. Their stars mixing together over hundreds of millions of years. The result will be a new, larger galaxy that astronomers have nicknamed Milkomda. Despite the dramatic language of collision, remember that galaxies are mostly empty space. The stars will pass by each other without touching, like two swarms of fireflies merging into one. Our solar system will probably survive the merger just fine, though we might end up in a different part of the new combined galaxy. There are open star clusters in the Milky Way. Loose groups of stars that formed together from the same gas cloud and are still loosely bound by gravity. The Pleiades, visible to the naked eye, is one of the most famous. These seven sisters, as they're sometimes called, are actually a cluster of hundreds of stars with about 7 bright enough to see without a telescope. Open clusters gradually disperse over time as their member stars drift apart, scattered by gravitational interactions with other stars and gas clouds. Eventually, the cluster dissolves, and its stars become part of the general stellar population. They were family once, siblings born together, but time and gravity slowly pulled them apart. The interstellar medium, the gas and dust between the stars, is incredibly thin. In some regions, there might be only 1 atom per cubic centimeter. A vacuum far better than anything we can create in laboratories on Earth. Yet, this thin material adds up over the vast distances of space. There's enough gas and dust in the Milky Way to make billions more stars. Raw material for future generations of stellar birth. This interstellar medium is constantly being recycled, material expelled by dying stars, enriching the clouds, which then collapse to form new stars, creating a cycle that's been ongoing for billions of years. There are supernova remnants scattered throughout the galaxy, expanding shells of debris from stars that exploded in the past. The Crab Nebula is one of the most famous. The remains of a supernova that was observed and recorded by Chinese astronomers in the year 1054. The nebula is still expanding today, still glowing from the energy of that long ago explosion. And at its center is a pulsar, the collapsed core of the star that exploded, spinning 30 times per second. These remnants are temporary structures, visible for thousands of years before they fade and disperse. But while they last, they're spectacular monuments to stellar death. The bar at the center of our galaxy is an elongated structure of stars that extends across the central bulge. Our galaxy is actually a barred spiral galaxy, meaning it has this bar running through its center with the spiral arms attached to the ends of the bar. The bar rotates as a unit, slower than the disk around it, and it funnels gas toward the galactic center. About 2/3 of all spiral galaxies have bars, so the Milky Way is typical in this respect. The bar gives our galaxy a slightly different character than a pure spiral, adding an extra element of structure to the galactic center. There are Wolf-Rayet stars in the Milky Way, massive stars that have blown away their outer layers through powerful stellar winds, exposing their hot cores. These stars are among the most luminous in the galaxy, shining with a light of hundreds of thousands of suns, even though they're relatively small. They're nearing the ends of their lives and will soon explode as supernovas. Dwarf stars are rare, only a few hundred known in the entire galaxy. But they're important because they represent a brief but spectacular phase in the life of the most massive stars. The rotation curve of the Milky Way is flat, meaning that stars far from the galactic center orbit at roughly the same speed as stars closer in. This is strange because in our solar system, planets farther from the Sun orbit more slowly, following Kepler's laws. The flat rotation curve of the galaxy is one of the key pieces of evidence for dark matter. The visible matter in the galaxy isn't distributed in a way that would produce a flat rotation curve. There must be additional invisible mass extending far beyond the visible disk. And that mass is dark matter, providing the extra gravity needed to keep the outer stars moving as fast as they do. There are cataclysmic variables in the Milky Way. Binary star systems where one star is a white dwarf pulling material from a companion star. As this stolen material piles up on the white dwarf's surface, it occasionally ignites in a thermonuclear explosion called a nova. These are smaller and less violent than supernovas, and the white dwarf survives to repeat the process. Some cataclysmic variables undergo nova explosions regularly, flaring up every few decades or centuries. They're reminders that the galaxy is a dynamic place where stars interact, transfer material, and sometimes explode in spectacular displays. The thick disk of the Milky Way is a population of older stars that orbit above and below the thin disk where most stars are found. These stars have random orbits that take them far from the galactic plane, creating a thicker layer of stars surrounding the thin disk. The thick disk stars are older and contain fewer heavy elements than stars in the thin disk, suggesting they formed earlier in the galaxy's history when the Milky Way was younger and less chemically enriched. Our galaxy has layers like an onion, each layer telling a different part of the galactic story. There are protoplanetary disks throughout the galaxy, disks of gas and dust around young stars, where planets are in the process of forming. Astronomers can now image these disks using powerful telescopes, seeing gaps and rings in the dust that mark where planets are sweeping out their orbits. In some disks, we can see spiral patterns or asymmetries that hint at planets massive enough to disturb the disk material. We're watching planetary systems being born, seeing the early stages of a process that created our own solar system billions of years ago. The Milky Way is a factory for making planets, and business is always good. Asterisk, the escape velocity from the Milky Way, the speed needed to completely leave the galaxy, is about 350 miles per second at our location. That's incredibly fast, much faster than any spacecraft we've ever built. The Voyager probes our fastest and most distant spacecraft, are traveling at only about 10 miles per second, nowhere near fast enough to escape the galaxy. They'll remain part of the Milky Way forever, orbiting the galactic center along with everything else. To truly leave our galaxy and travel to another would require technology far beyond anything we currently possess. There are reflection nebulae in the Milky Way, clouds of dust that don't glow on their own, but reflect the light of nearby stars. These nebulae appear blue because blue light is scattered more effectively than red light. The same reason our sky is blue. The Pleiades star cluster is surrounded by a faint reflection nebula, visible in long exposure photographs as a bluish haze around the bright stars. These nebulae are gentle reminders that space is not completely empty, that there's dust floating between the stars, and that this dust can create beauty when illuminated by starlight. The galactic year, the time it takes our solar system to complete one orbit around the galaxy, is about 230 million Earth years. Since our Sun formed, it has completed roughly 20 galactic years. When the Sun was born, the Milky Way looked subtly different, with stars in different positions, some having been born, others having died. Our solar system has made 20 trips around this vast cosmic carousel, witnessing the slow changes in the galactic landscape, where ancient travelers, our Sun carrying us on a journey that spans the history of complex life on Earth. Asterisk. There are symbiotic stars in the Milky Way, binary systems where a red giant star transfers material to a white dwarf companion, creating spectacular displays of light and gas. Unlike cataclysmic variables where the transfer is violent, symbiotic systems are gentler, with material flowing steadily from one star to the other through an accretion disk. These systems can persist for millions of years. The two stars, locked in an embrace, sharing material in a cosmic dance that will eventually change both of them. Binary stars often have fascinating relationships, their fates intertwined in ways that single stars never experience. The metallicity of stars in the Milky Way varies with location and age. Metallicity is the abundance of elements heavier than hydrogen and helium. What astronomers call metals, even though they include elements like carbon and oxygen. Stars near the galactic center and in the disk tend to have higher metallicity because they formed from gas that had been enriched by previous generations of stars. Stars in the halo and globular clusters have lower metallicity because they're older, formed when the galaxy was young and hadn't yet been enriched with many heavy elements. You can learn about a star's history by measuring its chemical composition. There are T Tauri stars scattered throughout the galaxy, young stars that are still in the process of forming, not yet settled into the stable main sequence phase where most of their life will be spent. These stars are variable, their brightness fluctuating as clumps of material fall onto them from surrounding disks. They have powerful, stellar winds and sometimes jets of material shooting out from their poles. T Tauri stars are what our sun was like about 4.5 billion years ago. Energetic youngsters still finding their stability. Watching these stars helps us understand how our own solar system formed and evolved. The Sagittarius dwarf elliptical galaxy is currently being torn apart by the Milky Way's gravity. This small galaxy is passing through our galactic disk, and streams of its stars are being pulled away and absorbed into the Milky Way. This process has happened several times as Sagittarius orbits our galaxy, and with each pass, it loses more material. Eventually, there will be nothing left of Sagittarius as a separate entity. Its stars will have become part of the Milky Way, immigrants from a smaller galaxy that no longer exists. Our galaxy grows through such mergers, consuming smaller galaxies and incorporating their stars into our growing population. There are orbital objects in star-forming regions, jets of gas shot out by newly forming stars, plowing into the surrounding gas and creating glowing shock waves. These objects are named after the astronomers who first studied them, and they mark places where baby stars are clearing out their surroundings, blowing away the gas and dust that might otherwise fall onto them. Orbital objects are temporary, lasting only a few thousand years before fading, but they're beautiful indicators of active star formation, signposts pointing to the locations of new suns being born. There are stellar black holes scattered throughout the Milky Way, the collapsed remnants of massive stars that exploded as supernovas, unlike the supermassive black hole at the galactic center. These stellar mass black holes contain only a few times the mass of our sun, compressed into an incredibly small space. Most stellar black holes are invisible, dark, and silent, detectable only when they interact with nearby matter. Some are in binary systems where they pull material from a companion star, creating bright X-ray sources as the stolen gas spirals inward. Astronomers estimate there might be tens of millions of stellar black holes in our galaxy, most of them lone wanderers drifting quietly through space. The solar neighborhood, the region of space within about 30 light years of our sun, contains only a few hundred stars. Despite the billions of stars in our galaxy, space is so vast that stars are typically separated by several light years. Our nearest stellar neighbor, Proxima Centauri, is about 4.2 light years away. If the sun were the size of a grapefruit, Proxima Centauri would be another grapefruit about 2,500 miles away. Stars are tiny islands of matter separated by enormous oceans of space. This emptiness is what makes space travel so challenging, and what keeps stellar systems isolated from one another. There are emission nebulae throughout the Milky Way, clouds of gas that glow because they're being energized by nearby hot stars. The Orion Nebula is an emission nebula, glowing red and pink from hydrogen gas excited by ultraviolet light from young stars embedded within it. These nebulae are often regions of active star formation, the glowing gas marking places where stars have recently been born. They're some of the most photogenic objects in the galaxy, colorful clouds that reveal themselves in long exposure photographs. Though they appear much fainter to the naked eye, the galaxy decorates itself with these glowing tapestries, art created by stars and gas interacting. The metallicity gradient in our galaxy shows that stars near the center have higher abundances of heavy elements than stars in the outer regions. This makes sense because the inner galaxy has experienced more generations of star formation, more supernovas enriching the gas with heavy elements. The outer regions are less enriched, their gas containing fewer metals. Our Sun, located in the middle regions, has a middling metallicity, about average for stars in its neighborhood. This chemical gradient is one way the galaxy records its own history, with composition revealing where and when different stellar populations formed. There are stellar populations in the Milky Way that tell the story of our galaxy's formation and evolution. Population 1 stars are young, metal-rich stars found in the disk and spiral arms. Population 2 stars are older, metal, poor stars found in the halo and globular clusters. And though we've never found them, population 3 stars would be the very first generation of stars, made purely from hydrogen and helium from the Big Bang. These different populations represent different chapters in the galaxy's life story, from its ancient beginnings to its current activity of forming new stars. The local bubble is a region of hot, low-density gas about 300 light-years across that surrounds our solar system. This bubble was created by supernova explosions that occurred in this region millions of years ago, clearing out the normal interstellar gas and replacing it with hot, thin material. We're living inside this bubble, floating in a cavity blown by long-dead stars. The bubble affects how we observe distant objects because we're looking through less dust than we would otherwise, giving us clearer views in certain directions. Even our local environment has been shaped by violent events in the past. There are high-velocity clouds in the Milky Way, clouds of neutral hydrogen moving at speeds different from the normal rotation of the galaxy. Some of these clouds might be material falling into the galaxy from intergalactic space, fresh gas that will eventually be incorporated into the disk and form new stars. Others might be gas ejected from the disk by supernova explosions, fountaining up into the halo before falling back down. These clouds show that the galaxy is not a closed system, but exchanges material with its surroundings, breathing in fresh gas and exhaling processed material in a cycle that helps sustain star formation. The Gould Belt is a ring of young stars and star forming regions about 3,000 light-years across, tilted about 20 degrees from the plane of the galaxy. Our solar system is located near the inner edge of this belt. Many of the brightest stars we see in our night sky, including most of the stars in Orion and Scorpius, are part of the Gould Belt. This structure might have formed from a collision between a gas cloud and the galactic disk about 30 million years ago, triggering a burst of star formation that's still ongoing. We're surrounded by a neighborhood of recently formed stars, all born from the same event. Asterisk, there are blue stragglers in globular clusters, stars that appear younger and bluer than they should be, based on the age of the cluster. These stars are puzzling because all the stars in a cluster should have formed at the same time. Yet, blue stragglers look like they're younger than their neighbors. The explanation is that they've been rejuvenated either by merging with another star or by pulling material from a companion. They're stellar vampires or merger products, stars that have found a way to extend their youth beyond what should be possible. The universe is full of exceptions and special cases, reminders that simple rules don't always apply. The rotation of the Milky Way creates open star clusters gradually disperse, their member stars drifting apart as differential rotation pulls them in different directions. Molecular clouds can be torn apart by the same shear forces. Even the spiral arms are constantly being reinforced by density waves because the shear would otherwise wind them up and destroy them. The galaxy is not a static structure, but a dynamic system where rotation and gravity are constantly competing, creating structure in some places while destroying it in others. There are pulsar wind nebulae in the Milky Way, glowing bubbles of material powered by the intense radiation and particles streaming from rapidly rotating pulsars. The Crab Nebula is the most famous example, its glow powered by a pulsar at its center that's spinning 30 times per second. These nebulae are like cosmic neon signs lit up by the energy of neutron stars, visible reminders that even the most compact remnants of dead stars can still affect their surroundings. They're beautiful and energetic, proving that stellar death can be as spectacular as stellar birth. The spiral arms of the Milky Way are not solid structures, but density waves, regions where stars and gas pile up temporarily as they orbit the galaxy. Stars move through these arms like cars moving through a traffic jam, slowing down as they pass through the denser regions. The arms themselves rotate at a different speed than the stars, maintaining their spiral pattern even as individual stars drift in and out. This wave pattern has persisted for billions of years, a self-organizing structure that emerges from the collective gravity of billions of stars. The spiral arms are where most star formation happens, because the compression of gas as it enters the arm triggers the collapse of clouds into new stars. They're like cosmic assembly lines, factories where the raw materials of space are processed into shining new stellar objects. There are planetary nebulae scattered throughout the galaxy, glowing shells of gas ejected by dying sun-like stars. These nebulae come in stunning varieties of shapes: spheres, rings, butterflies, hourglasses. Each shape determined by the details of how the star shed its outer layers. At the center of each nebula sits the exposed core of the original star, a white dwarf that's incredibly hot and bombards the surrounding gas with ultraviolet light, making it glow in brilliant colors. These nebulae are brief by cosmic standards, lasting only tens of thousands of years before the gas disperses into space. They're the final artwork of dying stars, beautiful monuments marking the end of stellar lives, enriching space with the elements created during the star's lifetime. The rotation curve of the Milky Way shows that stars in the outer regions orbit faster than they should based on the visible matter alone. This discrepancy led to the discovery of dark matter, invisible material that makes up most of the galaxy's mass. The dark matter forms a vast halo around the galaxy, extending far beyond the visible disk, its gravity holding everything together. Without this dark matter, the galaxy would fly apart, unable to hold itself together with just the gravity of stars and gas. We can't see this dark matter directly, can't touch it or detect it except through its gravitational effects. Yet, it's the dominant component of our galaxy. The universe is mostly made of something we can't see, a humbling reminder of how much we still don't understand. There are stellar streams threading through the Milky Way, ribbons of stars that were once part of globular clusters or small galaxies torn apart by our galaxy's gravity. These streams can stretch for tens of thousands of light years, wrapping around the galaxy multiple times, slowly dispersing as the stars drift apart. They're archaeological evidence, fossil records of the galaxy's violent past, showing us which smaller systems were consumed as the Milky Way grew. By mapping these streams, astronomers can reconstruct the merging history of our galaxy, identifying which of our stars originally came from elsewhere. The galaxy is built from the corpses of smaller systems assimilated over billions of years. their stars now calling the Milky Way home. The Milky Way has a thick disk in addition to its thin disk, a population of older stars that orbit with more random motions and occupy a thicker layer. These thick disk stars are thought to be some of the oldest stars in the galaxy, formed during an early period of more chaotic star formation, or possibly captured from smaller galaxies that merged early in the Milky Way's history. They contained fewer heavy elements than younger stars, showing they were born when the galaxy was less chemically evolved. The thick disk is like a fossil layer, preserving information about conditions in the early galaxy. Before generations of star formation had enriched space with heavy elements, there are hot Jupiters orbiting stars throughout the galaxy, gas giant planets that orbit extremely close to their parent stars, completing orbits in just a few days. These planets shouldn't exist where they are. They're too close to their stars to have formed there. So they must have migrated inward from farther out in their planetary systems. Their existence was completely unexpected when the first one was discovered, challenging theories of planet formation and forcing astronomers to develop migration mechanisms to explain how planets can move through their systems. These worlds are tidally locked, with one side always facing their star, baked to temperatures of thousands of degrees, their atmospheres probably being stripped away by stellar radiation. They're hellish worlds, teaching us that planetary systems can be far stranger than our own. The Milky Way's magnetic field threads through the entire galaxy, aligned roughly with a spiral arms. This field is weak compared to Earth's magnetic field, but extends over vast volumes of space, making it important for how gas moves and how cosmic rays propagate. The magnetic field is generated by the motion of charged particles in the galaxy, maintained by a galactic dynamo process similar to how Earth generates its magnetic field, but on an incomparably larger scale. The field affects star formation by providing pressure that helps support gas clouds against gravity, and it guides cosmic rays as they bounce through space. It's an invisible infrastructure, a galaxy-wide structure that influences countless processes, but that we can only detect through careful observations of starlight and radio waves. There are Wolf-Rayet stars in the Milky Way, massive stars that have lost their outer hydrogen layers and exposed their hot helium cores. These stars blow powerful stellar winds, ejecting mass at rates that would empty a sun-like star in just thousands of years. The winds are so strong they push back surrounding material, creating expanding bubbles of hot gas. These stars are in the late stages of their lives, racing toward supernova explosions, burning through their remaining fuel at prodigious rates. They're some of the hottest stars we know, with surface temperatures exceeding 100,000 degrees. So hot they emit most of their light in ultraviolet wavelength, invisible to human eyes. The Sun takes about 200 million years to complete one orbit around the galactic center, a period sometimes called a galactic year. In the entire history of Earth, our planet has completed only about 20 orbits around the galaxy. Dinosaurs roamed Earth just one galactic year ago. The last time we were at this point in our orbit, the galaxy looked essentially the same as it does now. The slow pace of galactic evolution means things don't change much in a single orbit. But over many orbits, over billions of years, the cumulative changes transform the galaxy completely. We're passengers on a cosmic carousel, slowly circling the galactic center. Our position in the galaxy constantly changing, even as we think of ourselves as being in one place. There are intermediate mass black holes lurking in the Milky Way. Black holes with masses between stellar mass black holes and supermassive black holes. These objects are rare and difficult to detect, but a few candidates have been found in globular clusters and the central regions of the galaxy. They might form from the collision of multiple stars in dense stellar environments, or from the direct collapse of very massive stars. They're missing links in black hole evolution, connecting the stellar mass black holes that form from individual stars to the supermassive monsters at galactic centers. Understanding how these intermediate mass objects form could help explain how supermassive black holes grew to such enormous sizes. The zone of avoidance is a region of the sky blocked by the Milky Way's disk, where dust obscures our view of distant galaxies. Looking through the plane of the galaxy is like looking through fog. This zone covers about 20% of the sky, hiding countless galaxies from our view. Astronomers use radio and infrared observations to peer through the dust, mapping what lies beyond, discovering hidden galaxies and structures that would be invisible in optical light. The galaxy itself blocks our view, a reminder that we're embedded within it, that our location shapes what we can see of the wider universe. There are blue stragglers in globular clusters, stars that appear younger and bluer than they should be, based on the cluster's age. These stars are puzzles. They shouldn't exist if all the stars in the cluster formed at the same time, as theory suggests they did. The most likely explanation is that these are stars that have been rejuvenated, either by colliding with other stars or by stealing mass from companions, gaining fresh fuel that allows them to shine brighter and bluer than their siblings. They're products of stellar interactions, stars with complicated histories, reminding us that not all stellar evolution is solitary, that stars in dense environments frequently affect each other. The Milky Way emits gamma rays from its center, high-energy light produced by interactions between cosmic rays and the gas near the galactic core. This gamma-ray glow traces the distribution of cosmic rays, showing where high-energy particles are concentrated. Some of the gamma rays might come from dark matter particles annihilating each other. Though this interpretation is controversial and other explanations exist, the gamma ray emission is a window into high-energy processes happening near the galactic center. Phenomena that would be invisible at other wavelengths. The galaxy glows in ways invisible to our eyes, revealing its violent and energetic nature. There are circumbinary planets in the Milky Way, planets that orbit around binary star systems, experiencing sunrises from two suns, like the fictional planet Tatooine. These planets face unique challenges. Their orbits must be stable, despite the complex gravitational influence of two stars, and the habitable zone moves in complicated ways as the two stars orbit each other. Yet these planets exist. Nature finds ways to form planets even in environments that seem hostile to planet formation. They're reminders that the universe is more creative than our imaginations, that planets can exist in configurations we might never have predicted. The escape velocity from the Milky Way is about 500 kilometers per second. The speed an object would need to completely leave the galaxy's gravitational influence. A few hypervelocity stars have been discovered traveling faster than this, ejected from the galaxy by gravitational interactions with the supermassive black hole or binary star encounters. These stars are being flung into intergalactic space, destined to spend eternity wandering between galaxies, forever separated from the Milky Way that gave them birth. Their galactic exiles, evidence that galaxies occasionally eject their own stars, casting them out into the cosmic void. There are starburst regions in the Milky, producing dozens or hundreds of stars in relatively small volumes. These regions are often associated with colliding gas clouds or regions where spiral arm compression is particularly strong. The intense star formation creates clusters of hot young stars that illuminate their surroundings, their light and stellar winds sculpting the remaining gas into fantastic shapes. These regions are short-lived by galactic standards, burning through their gas supplies in just a few million years. But while they last, they're among the brightest and most active places in the galaxy. The Milky Way has a subtle spiral structure, not as pronounced as some galaxies, but definitely present. The spiral pattern is maintained by density waves, self-sustaining patterns that persist even as individual stars and gas clouds move through them. The spiral arms are where most of the galaxy's star formation happens, where giant molecular clouds accumulate and fragment into stars. From outside, if we could view the Milky Way from a distant vantage point, we'd see a beautiful spiral pattern, arms winding outward from the central bulge, studded with bright blue young stars and glowing nebulae. We're inside this pattern, unable to see it directly, but we've mapped it through careful observations. reconstructing our galaxy's structure from within. There are stellar nurseries throughout the galaxy, where thousands of stars are being born simultaneously. Vast clouds fragmenting into countless pieces, each piece collapsing to form a star. These regions are chaotic, filled with competing processes, gravity pulling inward, while magnetic fields and turbulence resist collapse. Stellar winds from newly formed stars disrupting nearby regions, even as they trigger collapse elsewhere. The result is that star formation is messy, inefficient, with only a small fraction of a cloud's mass actually ending up in stars. Most of the gas is either dispersed by stellar feedback or remains in the cloud, waiting for another compression event to trigger the next generation of star formation. The Milky Way contains exotic objects we're only beginning to understand. Strange systems that don't fit into standard categories. There are magnetars with magnetic fields trillions of times stronger than Earth's. Thorn-Zitko, objects where a neutron star has been swallowed by a giant star. Planets wandering through space without parent stars. Stars made almost entirely of carbon and oxygen. The galaxy is a laboratory where nature experiments with every possible combination of matter and energy, creating objects at the boundaries of what physics allows. Each new discovery expands our understanding, showing us that the universe is stranger and more varied than we imagined. The local bubble is a cavity in the interstellar medium surrounding our solar system, a region about 300 light-years across, where gas is hot and tenuous. This bubble was excavated by supernova explosions over the past 10 million years. Multiple stars exploding and blowing away the surrounding gas. We're inside this bubble, in a region of lower density, and most of the nearby stars visible in our night sky are also within it. The bubble is part of a larger structure of interconnecting cavities, a foam-like arrangement created by generations of supernovas, each explosion creating its own bubbles merging and overlapping. Space near the sun is less dense than average because we happen to be in one of these evacuated regions. There are stellar black holes throughout the galaxy, perhaps 100 million of them. The collapsed cores of massive stars that exploded as supernovas. Most of these black holes are solitary and invisible, undetectable, because they're not actively feeding on anything. Only when they have companion stars do we spot them. When they pull material from their companions and the infalling gas emits X-rays. These black holes are fossils of massive stars, markers of where the most extreme stellar explosions occurred. They'll persist essentially forever, gradually evaporating through Hawking radiation, but on timescales longer than the current age of the universe many times. Over, the metallicity gradient in the Milky Way shows that stars near the galactic center have more heavy elements than stars in the outer regions. This gradient reflects the history of star formation and chemical enrichment. The center formed stars more actively and for longer, building up higher concentrations of heavy elements through repeated generations of stellar evolution. The outer regions are less enriched. Their stars contain fewer heavy elements on average, showing they've had less time or lower rates of star formation. This chemical gradient is a timeline written in stellar compositions, encoding the galaxy's enrichment history. There are stellar associations throughout the galaxy, loose groupings of stars that formed together but aren't gravitationally bound enough to remain together forever. These associations gradually disperse over millions of years. Their stars drifting apart as they orbit the galaxy at slightly different speeds. The nearest stellar associations contain many of the brightest stars in our night sky. The stars of Orion's belt are part of an association, as are many stars in Scorpius and Centaurus. These groupings are evidence of recent star formation, young enough that the stars haven't had time to drift far from their birthplaces. They're temporary families, siblings that will eventually be scattered across the galaxy. The Milky Way is moving through space at hundreds of kilometers per second, falling toward the Virgo cluster as part of the large-scale structure of the universe. This motion is imperceptible to us because everything nearby is moving together. But it shows up in measurements of the cosmic microwave background, causing a dipole pattern where one side of the sky is slightly hotter and the other slightly cooler due to our motion. The galaxy isn't sitting still, but rushing through space, part of vast flows of galaxies streaming toward massive structures. We're being pulled by the gravity of distant galaxy clusters, our trajectory set by the distribution of matter across hundreds of millions of light years. Asterisk, there are protoplanetary disks around young stars throughout the galaxy, flattened disks of gas and dust where planets are forming. These disks are the leftover material from star formation, the angular momentum of the original cloud causing material to settle into a disk rather than falling straight down onto the star. Within these disks, dust grains stick together, building up into larger and larger objects, first pebbles, then boulders, then planetesimals, eventually growing into full planets. The process takes millions of years, and we can observe it at different stages by looking at many different systems. These disks are planet factories, the birthplaces of solar systems, and studying them helps us understand how our own solar system formed billions of years ago. The bar at the center of the Milky Way rotates faster than the disk, driving gas inward toward the galactic center. This inward flow feeds star formation in the central regions and may also funnel material toward the supermassive black hole. The bar acts like a cosmic mixer, stirring the inner galaxy, redistributing material and changing the orbits of stars. Our sun is outside the bar in the more orderly disk, but the bar's gravity influences the motion of stars and gas throughout the inner galaxy. The bar is a dynamic structure, possibly growing over time as stars are captured into it, reshaping the galaxy's central regions. There are mass loss events happening constantly throughout the galaxy. Stars in their final stages shedding enormous amounts of material into space. Red giants blow strong stellar winds, losing substantial fractions of their mass over millions of years. Supergiants can lose mass even faster. Their powerful winds driven by intense radiation pressure. This expelled material enriches the interstellar medium, adding heavy elements created inside the stars during their lifetimes. Mass loss is how stars return material to space, completing the cycle of matter that flows from interstellar clouds to stars and back again. The galaxy breathes. Stars inhaling material at birth and exhaling it in death. The Milky Way's history is one of growth through mergers, absorbing smaller galaxies over billions of years. Each merger adds stars, gas, and dark matter to the Milky Way. But it also disrupts the existing structure, stirring up the disk and halo. The largest merger in our galaxy's recent history was with a galaxy called Enceladus, which crashed into the Milky Way about 10 billion years ago, leaving behind streams of stars we can still identify today. More mergers are coming. The Sagittarius dwarf galaxy is currently being torn apart and absorbed. And in a few billion years, Andromeda will arrive for a merger that will completely transform both galaxies. Our galaxy is not finished growing. It's still accumulating mass, still evolving. There are stellar winds throughout the galaxy, streams of particles blown off the surfaces of stars. Our sun has a stellar wind, the solar wind that shapes Earth's magnetosphere and creates auroras. But many stars have much more powerful winds. Hot, massive stars blow winds that can remove significant fractions of their mass over their lifetimes. Cool giant stars also blow winds, gentler but persistent, gradually shedding their outer layers. These winds carry away mass, angular momentum, and chemical elements, affecting stellar evolution and enriching the space between stars. The galaxy is filled with these winds, invisible currents flowing from every star. The future of the Milky Way is one of continued evolution and eventual merger with Andromeda. Over the next few billion years, the galaxy will continue forming stars, though the rate will gradually decline as gas is consumed and less material remains available. The merger with Andromeda will be a spectacular event. The two galaxies passing through each other, their stars intermixing, their gases colliding and triggering bursts of star formation. The two supermassive black holes will eventually spiral together and merge, releasing gravitational waves that will ripple across the universe. The result will be a giant elliptical galaxy. The stars from both galaxies mixed together in a new configuration, all traces of spiral structure erased. This new galaxy will be the final home for our sun's descendants. A different galaxy, but still carrying the legacy of the Milky Way. And so we reach the end of our journey through the Milky Way, a voyage across 400 billion stars, countless worlds, and structures beyond human comprehension. We've explored nebulae where stars are born, witnessed the violent deaths of massive suns, traced the invisible threads of dark matter holding everything together, and glimpsed the supermassive black hole lurking at our galaxy's heart. The Milky Way is more than just our cosmic address. It's our ancestral home, the place where the atoms in our bodies were forged inside dying stars, scattered through space, and eventually gathered into planets where life could emerge. Every element heavier than hydrogen and helium in your body was created inside a star somewhere in this galaxy, possibly billions of years ago, in explosions that seeded space with the raw materials for everything we see around us. Looking up at the night sky, that band of light stretching overhead is not just distant stars, but our family, our neighborhood on a cosmic scale. Those photons that reach your eyes have traveled for thousands of years, carrying messages from distant suns, telling stories of stellar births and deaths, of gas clouds collapsing and planets forming, of the endless cycle of creation and destruction that shapes our galaxy. We are made of star stuff, as Carl Sagan famously said, and we live on a small world orbiting an average star in the outer reaches of a typical spiral galaxy. Yet, from this modest position, we've managed to map the structure of our entire galaxy, discover its history, predict its future. We've reached out with telescopes and mathematics, reconstructing the Milky Way's past and forecasting its destiny billions of years from now. The galaxy continues its ancient dance, spiraling through space, growing through mergers, forming new stars, evolving in ways both gradual and catastrophic. In a few billion years, Andromeda will arrive, and our galaxy will be transformed, but the stars that exist now will mostly survive, continuing their orbits in a new configuration, part of a larger whole as you drift off to sleep. Remember that you are part of this vast cosmic story. The Milky Way is not something distant or separate from you. It's your home on the grandest scale imaginable. The same forces that shaped the galaxy shaped Earth. The same processes that create stars created the sun. And the same elements filling space fill your body. Rest well, knowing that you're connected to everything around you through bonds that stretch back to the beginning of time. That the atoms you're made of have witnessed billions of years of cosmic history, and that you're living in a galaxy more strange and wonderful than any fiction could capture. The Milky Way turns slowly overhead, indifferent to human concerns, but beautiful in its vast complexity. 100 billion stories written in starlight, waiting to be discovered. Sleep now and dream of spiral arms and stellar nurseries, of black holes and nebulae, of our galaxy in all its magnificent glory. Our island home in the infinite ocean of space. Good night, and may your dreams be filled with stars.